Hello everyone. So let's solve today's LeetCode POTD, a number of ways to divide a long corridor. So the problem states that we are given a long library corridor and there is a line of seats as well as decorative plants on this line. Now we are given a zero indexed string corridor which has a length n which only consists of these letters S and P, where S will denote the line of seat, means represents a seat, and P will be representing the decorative plants that we have. Now one room divider has already been placed to the left of index 0 and to the right of index n-1. Okay, so a room kind of thing has been made and there is a line of seeds and plants. Now we can install additional room dividers between the seeds or between the plants. Okay, so for each position between indices I-1 and I, so for example, if these corridors have already been installed and this is still 0, 1, 2 till n-1. So these dividers have already been installed. Now what we can do is we can install dividers from between any two indices, either between this and so on. Okay, so we have the liberty of installing dividers, and at each position only one divider can be, means at most one divider can be installed. So we need to divide the corridor into non-overlapping sections such that we divide in such a manner such that each section that is forming, it has exactly two seats. That means it should have only two S's and one P, for example here, and they can exist in any form. Similarly, if we again install a divider here, then the section that contains this should only have two S's, okay, and means P's can be anything. So we just need to make sure that the count of S or the count of seats is 2 only. Okay, exactly 2. So since there can be like multiple ways to perform the division, two ways are different if the position of dividers differ. So we need to return the number of ways to divide the corridor such that the conditions are satisfied. And since the answer may be large, because it can be really large if we try to account through all the possibilities in like a PNC manner. So we need to return it modulo 1 plus 7. And if there is no way, we simply return 0. So let's see the given input first. So we are given the seeds and plants in this form. So now these were the corridors which are already installed. Now since we want two seeds, how we can install the new corridor? Means we want two seeds in each section. So one thing that we observe is the total number of seats that we should have, seats should be even only. Okay, then only we'll be able to divide them into sections of 2. Now one divider we can place it here. So we see like in this section we have two seats, and in this section we also have two seats. Hence this is a valid divider addition. For here again we see this section has two seats and this section has two seats. So this is also valid, and similarly here we also see that this section has two seats and this section has two seats. So this is also valid. So this is, hence the output for this input will be 3 here, and we are able to satisfy because the number of seats were 4, which is even. Then only we are able to divide. Let's say another input. So here the number of seats is 2 only. Hence we cannot create a divider here. Let's say we create a divider here. So in this section we have 0 seats. Suppose we create a divider here. Then in this section we again have 0 seats. Suppose we create a divider here. Then in the section we again will have 1 seat, and in the section we have 1 seat. So both the conditions are not satisfied. Since there are only 2 seats, so we cannot place any divider. Okay, so hence the output here will be 1 only. And in this case we are given that the number of seats is simply 1, which is odd. And in odd cases we know that it is simply not possible, so we can simply return 0. Okay, so this in this one you may observe that we did not insert any observation, any dividers, but still the answer was 1. So we need to return the number of final final configurations which are valid, okay, by adding or not adding a corridor. Okay, so hence since this was a valid configuration, that's why the output here is 1. So what can we observe from this solution? So the first thing that we can think of is at each index, suppose this was the entire corridor, we have a divider at these places 0, 1, 2, 3 till n minus 1. So now at each position, either at this position or this position or this position, we have like the choice of either installing a divider or not installing a divider. Either installing a divider or not installing a divider, right? We have the choice here. And how we can maintain the choice? So what do we, when can we install a divider? When can we install a divider? So we can only install a divider when the count of seats from the previous section, after the previous section should be, means seats should be exactly 2. Then only we can install a divider, right? We can install. And if like seats is less than equals to 1, then cannot install. Cannot install. So based on these two conditions, we will try to like either put a divider or not put a divider and simply move forward. Okay. So what approach comes into our mind by seeing these choices that we have? It is means the question is simply asking us to apply dynamic programming. I hope like you were able to means observe that we need to apply dynamic programming here. If we didn't, then with time it will become more observant, because as we solve multiple problems, we have solved a lot of problems related to DP and observing. Whenever we have the choices, we tend to apply dynamic programming. Here also we'll try to do that, because the question is simply asking us to do that only. The question has the choices, and it is the parameters that will be changing here. Here the count of seats we need to account. So count of seats will be changing, which will be going till 0, 1 and 2. And similarly we'll be moving the index. So index will be changed. So what DP state can we create? We can simply create a DP of n cross 0, 1, 2, so 3. Okay. So where DP of ij stores the number of ways to, means number of ways to place corridors, place dividers till, means 0 till ith index, such that we have j seats in the current section that we are in. Means we have j seats in the current section. That means the last time that we placed a divider, after that we have the segment that we are processing, it has j seats. Okay. So this is what you mean by DP of ij. I hope thinking about this DP was easy for you. Now the next step is to identify the base case that we have. So what do we want? We want the answer for, means the entire string 0 till n minus 1, right? So the final answer will be storing in DP of n minus 1. And what do we want? That in the end, means j denotes that we have j seats in the current section. And for DP of n minus 1, this j should belongs to the last section. And then the last section, what should we have? We should have j equals to 2 only. That means last section should also have, means a number of seats equals to 2. Okay. So hence the base case will simply remain like if like index has crossed n means if index has reached here, then the last section that we should have processed. So if this seats that we have is seats is equals to 2, then only we'll be returning a valid way. Okay. And if in all other cases we'll be returning a invalid way of possibility. So we are trying to write the base case for the memoization function that we are going to write. Okay. Now once this is clear, so base case is clear, we try to find the transitions that we need to follow. Okay. And in memo function, what we have in the memo function, we have what? The index as well as the current seeds that we have. Okay. So now what can be the transitions that we need to observe? Okay, transitions. So in the case of where the number of seats is equals to 2, what can we do? In the case of seats equals to 2, either we can, means we will definitely need to put a corridor if the current section has seats equals to 2, and the next index is a s. That means we will definitely need to put a corridor here. Okay, because if we move forward without putting a divider, then the number of seats will become 3. Okay. So if like s of index is equals to s, then we'll definitely need to put a corridor, put a divider at particular index. Okay, so what we'll do, we'll like the number of ways that we have, suppose it is initially 0, so we'll need to increase our ways by what value? We'll call the memo function for index plus 1. Now index plus 1 means we will be putting a divider at this place. Okay, so that means the count of seats in our new section will become 1. Okay, index equals to 0 initially means we can put, suppose s was present at this place, so we can put a section at this place. Okay, so I hope it is clear. Now, so we'll calling a memo function for index plus 1 comma 1. Now, what if like instead of s there was a section seats equals to 2 and then p was present? So we have the choice. We have the choice of either putting a divider here or skipping it or not skipping a divider. Means not putting a divider here. Both are fine only. So else, we have the choice. So we have the choice of either putting or not putting. So it will be simply what? Either we will put it. So either we will put it. So that means index plus 1 comma 0, or will not put it, or will not put it. So it remains the index plus 1 comma 2 only. Okay, so these will be the number of ways. Means this will how will transition from seats equals to 2. Now what about the case where seats equals to 0 or 1? If the number of seats is equals to 0 or 1, then we simply know that we will not be able to place a divider currently. So we'll simply like else means seats equals to 0 or 1. In this case we know that we will not be able to put a divider. We can only move forward. So we'll see like if the s of index equals to s, then we'll what with the ways will become what? We'll call the memo with index plus 1 and we'll increase our seeds count by 1. Okay, because we are not able to put a divider currently. And else if it is p, then we'll simply like ways equals to what? We'll simply increase our index and the seeds count will remain the same only. Okay, so this is how the transitions will look for our DP array, and once the transitions are defined, then we'll be simply able to write the memoization function. And the initialization was also clear that DP of we need a DP of size n cross 3, and since n can go up to 1e5, so we'll simply like we can create a simple global DP array and initialize it with -1 and then write the memoization function as we simply do in all the approaches. So let's see the code for this approach and see if you have any doubts remaining. So we'll create these global variables so that we do not need to pass these DPs and strings and everything in the memo function or the solve function that we have. Okay, so we have created these global values that we require, the mod 1e9 plus 7, because this the number of ways that we add at each step. Okay, so we need to take it modulo %mod as well. Why? Because it may become the case that these values means becomes greater than integer range values int max. Okay, so hence we need to take mod at each step to keep it in the range of 1e9 plus 7. Okay, so this is why we have used this mod here. We have initialized this global DP with means we needed till 1e5. So we can simply like 10000. This is the size that we require. So we can simply replace this with 1, or we have used it till 5. And we initialize this global string so that we do not need to pass it in our memo function as well as this n. Now s will become corridor, n will become s dot size. We'll initialize the DP with -1 and call the function for till the 0th index, and we have 0 means 0 seats. Now what we do, if we reach the index n, then we check whether the count is 2 or not. If the count is 2, we'll simply return 1, else we'll return 0. If the DP state has already been calculated, then we simply return the count that we already have. Now the current base is 0 if the count of seats is 2. That means section is full, so we have a choice option. Place a divider before s of index. Okay, so if we place a divider before s of index, that means we'll be starting a new section. So if s of index is equals to s, then that means we'll be able to if it is equals to s, we'll be able to end this particular section. We'll be able to end this particular section by placing a divider here and move to index plus 1 with a number of seats as 1. Okay, so we'll do that here. And if else, if it is p, then what we'll do, we'll like means call the index plus 1 with zero count, number of seeds. So that is what we do, and that is what we discussed as well. Now the second case is where we in the p we do not like put a divider. We do not put a divider. So either we can like simply add base equals to base plus solve of index plus 1 comma 2, we can also write that, but this is written for the sake of clarity here. So don't place a divider, extend current section. So if s of index equals to p, we can simply extend. So it will be index plus 1 plus 2 comma 2. Now the case of where the counts of seeds is equals to 0 or 1. So in those cases we will simply not need to like we cannot put any seeds here. We cannot put any divider here. We need to extend the corridor that we have. So section is incomplete, 0 or 1. So we must continue. So if in s of index is s, we need to increase the count, else the count remains the same only. And in the end we'll be returning the dp of index comma count with equals to the number of ways. So this will be the overall approach for this problem, and this will be taking a complexity of big of n into 3, as well as the space required is also big of n into 3. So I hope you were able to follow along with the DP approach and how to think about DP states in these kind of problems. And once the DP state is clear, then writing either the memoization or the tabulation or the space optimized tabulation as well becomes very simple only. So let's try to submit this code and see how it works. This is the code that we have for this problem. Let's try to submit it and see. Yeah, so it runs in 95 ms because we have written a memorization function, so that is completely fine. Now talking about the like whether we can convert it into tabulation or not. So obviously we can, because we see like the current DP state is only dependent on index plus 1 and the count variables. Okay, so we can simply create a vector DP of size n cross 3, and we can call means simply call what we are doing here. We can simply convert it into iteration. So we have done it a multiple number of times. So I will not be explaining you that approach, because there exists another approach of solving it problem using PNC. So that's why I am not taking the tabulation as well as the space optimized solution. So we can simply know that since index is dependent on index plus 1, so obviously the index loop will be starting from what? N minus 1. So that the index plus 1 is already calculated. Now this will go till 0. Okay, and now since seeds are not, means either it can increase or decrease, so we can simply run this seeds loop, run this count loop from 0 till 2 or 2 till 0, both are same only. Okay, so this is what we'll do, and once we have these loops, we'll be following the same loop. Means if the count is 2, then we'll be means writing the same condition here, and if otherwise, then we'll be writing the same condition here. And in the end, the final result will be stored in dp of n minus 1. Means in the final result will be here, the will be stored in the memo function that we are calling. So initially it will be dp of 0 0. Okay, and then how we will be transitioning to normal space optimized one. So we know like dp of index is only dependent on dp of index plus 1. That means if we have this was index plus 1, so the result for dp of index is only dependent on dp of index plus 1, and these are only three values, 0 1 and 2. Hence instead of like maintaining the entire dp of size n cross 3, we can only maintain these three values. Okay, for 0 count, for 1 count, and for 2 count, and then we'll be able to calculate the result for this row. And once we have the result for this row, then we'll be able to update these three variables with the values of this row, and then we'll be able to calculate for previous rows. So similarly we can do that as well here. Now coming to the memoization, means the approach which we will use to solve it without using dp. Okay, so how do we solve it without using dp? We need to check that now. So like we know that whenever we want to find the number of ways or do something with which counts the number of ways of doing some task, then we, means if we want to use any other approach than dp, then maybe like PNC or some combinatorics formulae can be applied to solve it. Okay, so let's try to observe like whether means PNC can be applied here or not. So we know like if seeds count is equals to even, then only a result will be existing, right? If seeds count is odd, then we'll simply return 0. Okay, so we know that either means there are no seeds, there are means odd number of seeds, or suppose 0 seeds as well. In the case of 0 seeds as well, means even should be like greater than or equals to 2. If there are 0 seeds, means P, this is the case, then that means we cannot install any dividers, right? Because obviously this section will have 0 seeds and this section will have 0 seeds. So this is also not allowed. So in the case of odd as well as 0 seeds, we will be simply returning 0 only. And in the cases of even greater than or equals to 2, there only the means the solution will be existing. So what can we observe here? We know that we want to divide it into sections such that if we have the seeds S0, S1, then S2, S3, then till suppose suppose there are 2k seeds. So there will be like 2k minus 1 and S2k. Now what do we want? We it want to place corridors in such a manner such that these two are together, then these two are together, then these two are together, and till the end these two are together. That means we can only place dividers in between these places, means in between S1, S2, then S3, S4, and so on till what? S2k minus 2 and S2k minus 1. We can place a dividers between these places only, right? And now what are the number of ways of placing dividers between two indices? So suppose we have a seed at index suppose 1, and we have a seed at index means S0, this S1 is at index 1, and this S2 is at index suppose 5. So we had PP here, PP, P, okay, so 2, 3, 4. Now what are the number of ways of placing dividers? So either we can place a divider here 1, 2, 3, 4, right? So what will it will be simply index of S2 minus index of S1, right? That is 5 minus 1 equals to 4. Hence if we have the indices of these two seeds, then the number of ways of means putting dividers will be simply what? Index of Si minus index of Si minus 1. And now this I will be increasing it. Initially it is 2, so it will be increasing by 2. So we will be increasing this I by 2 at each steps. Okay. Now and at each step we know that since we need to account all the possible ways, and we know like placing a divider in between these places is not dependent on how we place divider between S3 and S4, right? So hence these all are independent events. Hence we can simply multiply their possibilities, means we can simply take multiplication of product of all their possibilities. So it will be simply the product of psi of I equals to 2 till I equals to 2k minus 1. Okay, and at each step will be increasing I by 2, and this is the final means the formula that we get. Okay, so I hope like you are able to follow with the approach that we tried to follow. Since there were independent events, we can simply take the product of all the possibilities, and that will be stored in our final result. Now either we can like store these indices of these all the seeds in a means in a separate vector in seeds, and then we can apply this approach of seeds of I minus seeds of I minus 1. We will be easily able to get that. Or we can like simply use two variables as well, like which maintains the previous seed encountered, and then we see like whether the previous seed encountered was the second seed, then we have the current seed, and then we'll be able to use current minus pref. So then we'll be able to do it in constant space. So like both approaches are fine. We do not have the constraint of like avoiding this space at any cost. Okay, so either we can simply use means store all the indices of seeds in a vector in seeds, or we can maintain two pointers where the previous seed will be corresponding to the previous means the second occurrence of the seed and the current seed that we have, and if the previous was the second occurrence, then we'll simply like either what we am asking you to say is S0 S1. So initially when we encounter the first seed, we'll make prev as -1. Okay, then we encounter, means if prev is -1 and then we encounter a seed, that means prev will become I index. Okay, now when we encounter a seed S2, we know that prev is not equals to -1. So hence that means we need to account its possibility. So we need to simply what? Current minus prev. And now again what we'll do, we'll update prev with -1 and move current forward. So this is what we can follow, and this will be simply done using constant space as well. So both are fine. Let's see the implementation of this logic, and it will get clearer in your head. So we have, like, I will be pushing all the indices of the seeds in the seeds vector, and the space optimization solution is also clearer now. So we see, like, whether the corridor of I is equal to S, so we push it in seeds. Now we need to see the edge conditions. So edge conditions are if the seed size is odd or it is equals to 0. So if any two of these conditions are true, then we simply need to return 0 only. Okay. Now comes the case of, like, at each step, what do you need to do? We need to multiply all the possibilities. So at each step, we find out the current length, seeds of I. We start from 2. We started from 2. We see, let's see the formula once again. So what is the formula? We started from 2, we move till 2k minus 1, and at each step we will be increasing I by 2 only. So this is what we do. We'll start I equals to 2, go to till less than seeds of size, increase I by 2 at each step. The current length will be seeds of I minus seeds of I minus 1. The current answer will be updated with answer into length percent more. And finally we will be returning this answer. So this will be like, again, the big of n approach. We have got rid of the big of 3 thing that we did initially, big of n cross 3, and we can simply, like, get rid of the space that we have used here of seeds using, like, prev and current pointers. Okay, so I hope the approach means all the approaches were clear to you. Like, this was means pretty simple to observe that this is a DP problem. So maybe it can be tagged as a medium as well instead of hard. Let's try to submit that code as well. So this is the code. Let's try to initially the DP solution ran in 95 ms. So let's see whether it performs better or not. As you can see, like, it runs in 29 ms, which is fast because of, like, initially we ran into the recursive text space, so maybe that's why it runs faster. So this was the overall approach for these problems. I hope you were able to grasp through all the approaches, and if you did, make sure to like as well as subscribe. And if you have any doubts remaining, feel free to comment down. I will be happy to help. Thank you so much for watching.